Okay, sir.
Yeah. Okay. So good afternoon. We will start with one more concept, which actually it is a request to come. What I thought is the K.B.N. college is offering BSc graduate program in data science. Those students are also involved in this particular training program, data science program, so that they can have some exposure towards one important advanced technique. Along with that, a request was made by one of the participant about a technique called multivariate analysis of variance. Okay, so today we are going to understand when we go for multivariate analysis of variance, what actually it stands for, and how the analysis of multivariate analysis of variance can be handled in R, and how to do pairwise comparison test, how to understand the outcomes of multivariate analysis of variance. All these things will be covered, okay, step by step. So keeping in view of the data science program and the statistics, especially I am witnessing, I am observing majority of the participants are also from who have completed masters in statistics, and who are doing masters in statistics, and some faculty and research community is also there. So hope this topic might be helpful for those people as well as for the young minds who wish to pursue statistics as their master's program. Okay, so this is a kind of exposure that how multivariate analysis of variance looks like, and when we go with multivariate analysis of variance. So I'll start my sharing the screen. Okay. Mm, sorry. Fine. Now, just a recall for a minute that now what will happen, we have taken the pond data where we have pH levels of each four independent ponds. So we started gradually increasing the data design and understood, suppose if I have nasal height, here I am taking a very well-known example data set, that is what we call Egyptian skull data. Okay, it's a very old data set and very widely used data set. It is openly available. Just you type in Google Egyptian skull data. Okay, so there one of the measurement is nasal height. This is what we call nasal height, and then the data pertaining to nasal height is covered across 4000 BC, 3000 BC, 300 BC, 850 BC, 200 BC, and 150 AD. Okay, now for a recollection of the discussions what we have done, suppose if the nasal height is observed only at 150th AD, I want to measure it is almost equal to 55. Uh, 55 is the value. Okay, okay. Then what will happen if I am collecting only one particular time point of time point at nasal height? That is what we call the one sample t-test. Okay, one sample t-test. Suppose if I add 2200 BC also, then this is one time period. This is another time period. A different set of samples are taken to collect the data pertaining to nasal height. Then I have two independent time periods, that is 150 AD and 200 BC, where the samples are independent to each time period. Then I wish to compare what is the average nasal height when compared to 200 BC and 150 AD. So what will become? So this problem will become two sample t-test. Okay. Now, more than if I add 1850 or if I add just 1850, now the condition should prevail in your mind that now the total independent groups are more than two. Then when it is more than two, it is the concept of Anova. Now I have added one term prefix to the Anova, what is called univariate Anova, because over these different time periods, years of time, nasal height alone is measured. Let us suppose nasal height is alone measured. Okay, then then single variable is under steady consideration across different years of time. So such thing is only one variable that is univariate, but that same variable should be compared across the different years of time. So such kind of a design, what we call is univariate ANOVA. Now we will extend. So far what we have seen, we have taken one variable at hand and started adding factor by factor. First year, 2 years, 3 years, 4 years, 5 years. So this is the design extension of the design in terms of the factors, populations we have done. Now, but in a practical scenario, we won't come across with a single variable. Okay, suppose I want to measure the cardiac profile, then immediately a 5 ml of blood sample will give me the total profile, what is called lipid profile. Lipid profile will tell how your HDL, high density lipoprotein is there, how your LDL, low density lipoprotein is there, how your VLDL is there, how about cholesterol, how about total triglycerides, okay, all these parameters. So now the decision making with respect decision making in statistics in every domain is not will not be able will not be easy. I mean, will not be apt if I talk on only one particular variable. Hence, the practical situation will prevail to handle multiple variables at a time across different populations. Okay, suppose let us see HbA1c, I said, or if you see any kind of another clinical profiles, it vary from region to region. WHO standards does have something like that. Okay, fine. Now coming to the Egyptian skull data, for instance, we have taken that only nasal height is measured across different years of time. Apart from nasal height, if I have the data of breadth, length, and some other thing, then what we have to do, we have to collectively make use of that particular multivariable characteristics of the skulls and then start comparing across different years of time. Now looks like when you visualize this kind of explanation, looks like little clumsy. Let us have the table now. Okay, this is the total snapshot of the samples of 150. That is, this is breadth, height, length, and nasal height. Okay, so four characteristics are measured on every skull over the years. Now see the data design variation. We had only one variable, but different years of time. Even this also has a subparts, right? Suppose if I consider only 150 AD, it will become one sample. If I consider two population, it is two sample t-test. If I consider more than two populations, two different years of time, it will become ANOVA. But in all the data design, extension of data design with respect to the multiple population, the variable under consideration is only one. But now, along with the dimension increase of the number of years of time, the dimension with respect to the measurement is also enhanced, I mean increased by, that is, breadth of the skull is also measured, height of the skull is also measured, length of the skull is also measured, and height is also. So each skull has a profile. Profile is nothing but a set of measurements pertaining to one particular individual who belong to this 4000 BCE. Okay, so this each row is named as a profile. Each row is named as a profile. So this kind of a structure where you have multiple characteristics to be handled at a time across comparing, I mean, we have to compare all these variables across different years of time, then such technique is called multivariate analysis of variance. So here the covariance structures do come. Why the covariance? What do you mean by covariance structure? It is a square matrix which will have, suppose here we have four variables. It is the 4 cross 4 square matrix. Diagonal elements are the variances corresponding to breadth, height, length, and nasal height, and the non-diagonal elements are the covariances between breadth and height, breadth and length, breadth and height. Okay, all pairwise combinations of four characteristics will be in the non-diagonal element. If you recollect, this covariability is observed graphically in car plot. Okay, we had ellipsoids. Whenever the strong correlation is there, whenever the strong correlation is there, the ellipsoid was so thickened and closer, and it was pure elliptical. Okay, now take that into consideration. How you compute R? Correlation is nothing but covariance of xy by sigma x into sigma y. So the covariance in the numerator part will play a prominent role in explaining the relation of intensity between those two. Okay, now you are able to catch up the link, how the correlation and how the ellipse, and now how we are observing this multivariate structure. The main essence of this multivariate structure comes with the two important, an extension of mean and standard deviation is called mean vector and covariance matrix. Mean vector is a kind of a column vector or a row vector, column vector, that it will have the average of breadth, height, length, and nasal height. Covariance structure will have the variances in the diagonal of each characteristic, and non-diagonal will have the combined variation. That means the variation observed between, I mean, the spread of the data, how the pattern of the data observed between breadth and height, height and nasal height, length and nasal height. Like this, all four C2 combinations will be depicted in a numerical quantity. So multivariate analysis, this is a beginning of the understanding of multivariate scenario, that multivariate ANOVA is the way where you have multiple characteristics at hand, and these characteristics as a set to be compared across different years of time. Okay, so this is what we call one-way MANOVA. I can shortly write this as M ANOVA, that is MANOVA, but now it is MANOVA, one-way MANOVA, because all these set of vector of variables x, I can now mathematically define capital X is equal to x1 comma x2 comma x3 comma x4. Each x1 x2 x3 x4 corresponds to MB BH BL NH. Now x is a vector. Now for that vector, the factor variable under consideration is year wise, according to the year, this vector to be compared. So only one kind of a variation is observed, that is what we call one-way MANOVA. Similarly, if I have different regions or any other thing, then that will become two-way, two-factor MANOVA. As we have one-way ANOVA, two-way ANOVA, similarly here also we have one-way MANOVA, two-way MANOVA. Only the major difference, that's what I'm telling, that in univariate ANOVA you will be having one variable and consideration. In multivariate ANOVA you will be having a set of characteristics, a vector of characteristics that are to be compiled for comparison across different years of time. So with a small introduction to the multivariate analysis of variance, we'll go further to understand the R codes behind this particular MANOVA, and then slowly one by one, we'll try to execute and understand the outputs as well. Okay. Now by this time you must have little exposed and well versed with how to import the data file. Right here, what are the different, for a minute time? Can we recollect? One form is read.csv file.choose, header equal to true. Okay, the other form is read.csv, working with a directory and giving an argument called header equal to true. The other form is what we have practiced these days is using a library read Excel and using a function read underscore Excel and giving the working directory where you can choose the data set in which sheet you have stored. Okay, now I am using one of that particular importing method, that I am stored this Manova skull data with a file name Manova skull data.csv, and it is stored in the working directory what you are viewing in the screen now. So read.csv is that. Fine. Now, first I said, whenever you want to do any kind of a statistical technique, I repeat again, that the first practice is to visualize the data, then calculate summary statistics, then apply, basing on those information, which you have muddled up with the graphical technique and data, this summary measure. Then you draw inferences using an appropriate statistical technique. Okay, fine. Similarly, we are doing the same, that we are trying to first visualize the data and print the summary across across the years, and then these are the two lines that a simple scatter plot. This plot of thing will give us a matrix scatter plot across breadth, height, length, and nasal height with respect to 5 years of time. 5 years of time. Now print summary. Summary is for what? Summary is for obtaining the mean, median, first minimum, maximum, first quartile, and third quartile of the total matrix of the data frame. Okay, now this is very clear by this time now. Now come on, now we'll use how to do Manova. Why we have decided Manova? Because in this particular Egyptian skull data, we have four variables at character at hand, and one variable, which is a factor variable that we have to define, which is to be compared. These four variables that are to be compared across the different years of time. That's why we have chosen a technique called Manova, and a function that to do Manova is M Anova. What about the function to do Anova? It is AOV. Okay, the function to do simple univariate ANOVA is AOV, but now to do the MANOVA, multivariate analysis of variance, you have a function called MANOVA. Okay, now I'm binding the columns to make it as one particular data frame. Okay, and modulo operator is for what? Modulo operator is for what? That these matrix form should, I mean, take the information in this particular binded matrix form and compare across here. And where the data is stored? Data is stored in MD. MD is nothing but Manova data. Okay, just for easy understanding, I'm taking MD, OD, something like this. Okay, now all the results are stored. There are two different representations. We can use that as all results are stored in P dot Manova, or we can change this as uh, MRES, Manova results. Okay, we can make it as MARES. Now hereafter we have to change this as here. Okay, let it be P dot Manova. It will take time now, because where and where I have used this P Manova, I have to call everywhere that one. Okay, all the results are stored in P dot Manova, and if you display this, it will show you the total sum of squares over the different factors observed. The summary of P Manova will give us the significance that whether each variable across the different variables is I mean, this is the overall MANOVA, where the total, there exists any difference between these parameters over the years. Now, we have one more function called summary.avov of the P MANOVA. What does it stand for is, here, this is the collective MANOVA table, which will talk about the, what we say, this covariance structures. Okay, covariance between the factors within the factors. Like in ANOVA, we have treatments. I mean, the factor sum of squares due to variation due to factor, and then residuals. Similarly, in one-way MANOVA, we have the sum of squares, the covariance covariance structures with respect to factor and error residual. Okay, now, but this function will enable us to see, take one variable of this particular vector and apply ANOVA to it, because whatever the multivariate technique you do, finally, to see whether each variable is significantly different with respect to the factor under consideration. This summary.ANOVA will tell you that taking one MB and compares across the years, take BH, compares across the years. Like this, how many variables you have in the data, for every variable, the output of ANOVA do come, because we need to see that whether each variable has its significance or not. we will understand, we will better understand once we execute this. Now, I want to once the model is built, the p-value should be interpreted for accepting or rejecting the null hypothesis, not accepting the null hypothesis. But however, once we won't, once we fail to accept the null hypothesis, then automatically we need to represent that particular differences with respect to the support, with the support of summary statistics. Okay, there are two different ways we have seen this usage. We have seen the usage of this by function by MD of the first four variables across year and generate the summary statistics. What this summary will give us? It will give us the five measures: mean, minimum, maximum, first quartile, second quartile, minimum, median, and mean. But I wish to present only the mean values for every variable across the years. Now, how to do is, this is the width function with the data set MD. T apply is one other new function where you take the variable MB and across the year compute the mean. Similarly, just change the variable name and remaining arguments will remain the same. So this will give us that for every variable across the years, means will be printed. Means will be printed. Further, whether the Manova is significant enough or not, we use a test called Pillai's test. Okay, Pillai's test is for testing across the years. Okay, now once the output is done, significant is done, finally we have to sort out with pairwise comparisons. We have to sort out with pairwise comparisons. So when you come to pairwise comparison, there is no, to the best of my knowledge, there is no any particular test for uh, taking all the variables at a time and comparing in the multivariate setup. All the multivariate analysis reduced to univariate setup in conclusion part. Okay, for example, you have might have worked with logistic regression, you might have worked with the discriminant analysis. Okay, whenever you, I mean, with a huge data set and multiple variables, you build a model. Finally, using that model, you will have a discriminant score on the left hand side, right? So using that score, you will be classifying the future objects and allocating the future objects. Now the entire multi-dimensional multivariate setup has reduced it to a univariate information, that is discriminant score, for further decision making. Likewise, here also, to have a proper pairwise comparison across the years with respect to MB, with respect to height, with respect to length, and with respect to nasal height. So that's why we have to do four independent pairwise comparison, one for each particular variable. Okay. Now, how to present the data? Okay, box plot, MB across years, BH across years, BL across years. So these graphs are for a recollection for you to how to project the box plot with respect to the variable across different factors, levels of each factor. Here, this box plot will generate, this line of code will generate a box plot that the varying values of MB across the years and with the by taking the data which is stored in MD and the labeling the x-axis as year and y label as MB. Okay, so this is the simple code. This is the simple code what we can understand. We are practicing this and we are making use of this code from day one to till date. Okay, till today. Okay, now what we do is we'll copy all these things into R and then start understanding step by step what actually each line of code will give us and how to make a proper interpretation out of that particular output. Okay, let me say copy all the things. Okay, new share. Where is our studio? Here it is, our studio. Now I have pasted, because now already we have seen all the codes what actually they stand for. Let us start one by one. Let us have some space for plot view so that we can have a better visualization of that particular scatter plot. Now loaded the data, I can see this is the first 6 records of the data, and then print summary. This is the overall summary. This is 1 to 4 only. Okay, using by function, we can define the mean and values at the bottom. It is there, but on the whole, this is the summary part. That minimum breadth of is observed in the data is 119, maximum is 148, and for every variable, this is the minimum and maximum that we have noticed. Okay, now let us plot this. Let us plot this. See what we're trying to understand here. Does the plot will give some information when conducting comparisons? Yes, because if you see these three, last column, they are related to MB, nasal height, breadth, height and nasal height, breadth and nasal height. They are totally scattered around. They are totally scattered around. But if you observe these two, the increasing in length, there is a gradual increasing in height also. Okay, and increasing length, there is a decremental in the breadth of the skull. Okay, most of the points. Okay, and then similar to this this thing, increasing height and increasing length. Okay, this is a one observation. It is not mandatory that you should have a graphical thing, but to make ourselves comfortable that what sort of a patterns relation is between observed is between length and height and breadth, and mathematic breadth and length. Okay, but the rest of the page, like height and breadth and nasal height with respect to other three, are totally independent. Okay, so why I am focusing these two is that over the years, as the length increase, there might be a gradual increasing in the height, but the breadth of the skull has gradually decreased over the years. Okay, just to make an observation. Now let us let us compute the Manova, and this is what Manova stands for. Okay, these are all the sum of squares due to each factor and then residuals, but more understanding will get summary of Anova. Yeah, this is summary of Anova. Summary of Anova. To compare more than two groups with a multivariate, you can do with Pillai trace, Royce trace, Hotling's thing, right? In multivariate analysis technique, comparing two multivariate vectors, two populations with respect to multivariate, we go with Hotling's t-square test. Okay. Apart from that, we can have this Pillai's test also, uh, and then Roy's test is also there. So different tests are available to compare the years across the data matrix what we have. So this showed a significant p-value. This showed a significant p-value indicating that these four measurements on the whole, okay, these four measurements have a variation over the years. The significant p-value indicates us or gives an information that over the different years of time, the measurements have a difference, maybe incremental or a decremental, okay, or they have some change in their measurements. But to see to see in each variable whether that significant is noticed or not, for that purpose we have to use summary of ANOVA. Now when we do summary of ANOVA, you see it started with MB, it compared across the group, across the years. So here it is significant p-value. Now coming to height, significance is noticed, which is very close by. There was a question in the previous sessions that if the p-value is very close, then how to understand it. Okay, and then we will address that. And BL is highly significant, means that there is a huge difference with respect to length of the Egyptian skulls over the years. And coming to nasal height, it is insignificant. See, when we did this overall Manova, we had an impression that the difference might exist in almost all measurements of the skull data. But when we did the same thing, we understood. The result came out in a nice way that over the years there is no change. On an average, there is no change in the nasal height, but there is a significant impact in the length of the skull over the years, okay, as well as height, and then as well as breadth. So of the four characteristics, breadth, height, and length have changed over the years. That is one conclusion we can make. Now, the next question will come. What is the next question? Which pair of ears where MB is, breadth is observed to be similar or not? We have 5 years, 5C2, 10 combinations will come. That is 4000 BC to 3300 BC, 4000 BC to 1850, 4000 to 200, 4000 to 150. Like this, all pairwise comparisons to be compared, because this result will tell us that MB, the breadth is varying across the years, but we do not know. So far, we cannot answer the question that does MB average breadth is same in which pair of years do differ significantly with respect to breadth, that we cannot address with this particular p-value. That's why when we do ANOVA or when we do MANOVA, there is a quite important, this is quite essential to land up with a pairwise comparison test, provided if significant p-value is noticed. If significant p-value is noticed, it creates one more investigation question, that which pair of years does the average MB value has a difference. Okay. Similarly, with respect to height, here the p-value, if you see 0.048, almost close to zero, not close to 0.05, but still we need to reject. We need to reject the null hypothesis. We should not accept the null hypothesis that average height across the years is almost similar, because numerically when we quantify it is less than 0.05, okay. And then but still we can verify what when we convert this, when we take the support of pairwise comparison, automatically that 0.05 will get divided by 5. Now the p value at comparison in pairwise test is 0.01. Definitely there the height might satisfy that no, there is no difference, average difference in the height across different pairs of years of time. Now let us go, hope you understand this output. Okay. Now let us go a little ahead about understanding, displaying summary statistics. See, this is across years, 150 AD. The average, now let us see this. Yeah, there was no difference, right, in nasal height. Look at the mean, 51.37, 51.97. Now little more, 50.57, and then 50.23. Look at the means of nasal height across the years. And one more is there, 4000, that is 50.53. See, 50.53, 50.23, come to the BC to AD. 50.53 was the average nasal height in 4000 BC. And then during 3300 BC, it was 50.23. Now in 1850 BC, it was 50.57. And then it is around 51.97, and then it came to 51.37. So across the different years of time, the mean differences is not that important. That differences will not give us any evidence that nasal height has changed across the years. That's why disclosed differences, the nearby differences of these means across the years, has resulted with insignificant p-value in the previous step. Now, whereas this length you see, length was observed to have a huge impact, right? Now 99.017, 99.07, 96.03, and then 94.53, and then 93.5. Here, with respect to length, even this measurement of, here you see 96 drastically changed with 94, and then it came to 93. So over the years, there is a gradual declinement. There is a, on an average, there is a gradual declinement in the length of the skull. Coming to the height, 133, 132, 133, 132, 130. So the closeness of this particular, the differences which are very close by might have resulted with respect to variation of natural variability observed along the data. But still, we are describing the data, but not we are drawing the conclusions. The conclusions can be drawn with the pairwise test. Okay. Now, um, we'll have the means this, with MB, BH, BL, and NH. Okay, if you want to depict only means, we can do display also. Anyway, we have done this already. We have done this. Now we'll start with pairwise test. We'll start um, with MB first. Okay, MB first. Let us understand. Now this is the pairwise comparison table. This is the pairwise t dot dest. Okay, this p-value is between 150 to 200. This p-value is between for 150 to 1850. This p-value is for 150 to 3300. And this p-value is for 150 to 400. Now, where and where that significant impact is there? What do you mean by significant impact? What is the alpha to be compared here? 0.01, not 0.05. Okay. Now, when we take the 0.01, only these three will come into the picture. Not even this. Not even this. Because 0.0167. So that's why we neglect and take this into accepting that the average breadth compared with 150 AD and 3000 BC do not differ. Do not differ. Okay. But now when we see these three p values, sorry, even this will also not come. Only two. Only two. That is, the average breadth of the skull varied from 4000 to 150 AD and 4000 BC to 200 AD. What does it mean? That in the duration of 4000 BC, 3300 BC, 1850 BCE, these three generations, there is no change. There is no change, that much change, noticeable change with respect to the breadth of the skull. But whereas that significance noticed from 2000 BC onwards, from 2000 BC onwards. Now coming to this height. Height. See, now you can link that p-value to this outcome. What was the p-value? 0.0487. There we rejected, though we rejected there, but the family-wise that 0.01 is giving a proper clear understanding that there is no difference. There is no difference of the average height across the years. Look, no p-value is less than 0.01. No p-value is less than 0.01, implying the meaning that across the years, several years of from 4000 BC to 150 AD, the average height remained same. So the change so far what we have witnessed is with respect to breadth. Now let us see with length. See, there is a huge good amount of results observed here. Look at the bottom, this line, the third line, and fourth line. Oh, even a third line and fourth line. The rest of the things are insignificant. What do you mean by insignificant? there is no change in the average length of 150 BC to 150 AD. Now look at this. 3300 BC to 150 AD, there is a significant change in the length. Significant change in the length. How to understand this? Now let us take 3300 and 150. Where is the mean of length? This is the mean. Okay, 99.16 to 93.5. The reduction of this 5.8 or some decimals is really a noticeable impact in the generations of having reducing length of the body. Okay, now uh, look at this 4000 to 200, even that is also significant. 3000 to 200, even that is also different. But that's why length has very important role in comparison the skulls across the years. Now let us do verify, because we got, with respect to nasal height, we got insignificant p-value when we compare. But still, let us see for some more understanding, some more better understanding. Let us run the pairwise dot. All the p-values are greater than 0.01. All the p-values are greater than 0.01. So what we are trying to understand here, what is the total summary, what we can make out of the outcome of Manova, outcome of summary dot AOV, and then how with the help of pairwise dot test. So we can make a simple line like this, that on an average, the nasal height and height has no different statistical difference across the years from 4000 BC to 150 AD. Whereas there is a gradual decreasing of average length and as well as breadth across the breadth also decreases, right? Breadth increased, breadth of the skull increased, length of the skull decreased over the years. So doing these many mechanisms, we are nicely able to argue, confidently claim that the length of the skull from 4000 BC to 150 AD gradually decreased, whereas the breadth of the skull gradually increased from 4000 BC to the 150 AD. What are the data what we have? Now, the same can be depicted graphically. The same can be depicted graphically. That first we'll let us partition the data, or we can understand one by one. I have not run this. Okay, let me share this in new share. I hope you are observing the panel where we have uh, this is for length, this is for breadth, this is for height, and this is for nasal height. Now, what are all observations we made so far? Now it is clearly visualized here. See, the nasal height across the ears are more or less nearer to each of the pair of mean differences. Okay, even height looks the same. Now, breadth, we said it gradually, I mean, this 150 year gradually increased. Look at this. This was at the lower around 130, it is around 132, and then this is around 135, and this is around 136. So there is a gradual increment in the average height of the breadth over the years. And coming to this length also, there is a gradual decrement. See how we have to connect. This is the practice. Once you sit in front of a data, all the observations you have, what you have made step by step, step by step, you have to collectively make that, and finally all those things should be clubbed up along with the p-value, graphical understanding, the means, okay, all the numerical outcomes to the best of the practice, that all the numerical outcomes should be taken into consideration to bridge them, to connect them for a nice report writing. Now, finally, one summary, what we can tell is that how to write the final output for this is the four characteristics were compared across the years and it was found to be significant. Now, using another function, we try to observe whether there is that particular significant is observed in each of the four variables that are in the data. Now, when we observe that each of the variable across the different years, we notice that except nasal height, the remaining three characteristics observed with a significant p-value less than 0.05. However, upon the descriptive summary and pairwise comparison test, it is evident that this height and nasal height do not differ on an average do not differ across the years, but there is a gradual incremental in the breadth, average breadth of the skull over 4000 BC to 150 AD, and there is a gradual decrement of length from 4000 BC to 150 AD. See, that means over the years, the Egyptian generation have a reduced length of the skull and as well as breadth of the skull. Okay. Now, this is the overall findings what we have uh, observed from this particular data. Okay. Now, what is the time? Are we on time? Hopefully, yes. Now it is up to the uh, participants. Now they can raise a question. Do you have any questions to raise? Oh, already they are ready. Okay. So what is the basic difference between univariate and multivariate data analysis? That is, sir, when we take single variable for comparison for building a model, okay, leave about regression. Regression start with the bivariate, okay. A regression starts with a bivariate. All the inferential statistics, okay, probability fitting, all those when we handle with single characteristic, then such kind of a thing is what we call univariate. More than one variable, it is bivariate. Two variables at hand is a bivariate, and when it is more than two, then it will become the multivariate data setup. Okay. Canonical correlation we can make. I don't have idea how to do a canonical correlation. Sorry, but I will check. I will check and let you know. Okay, correspondence also I have to. I think there is some your package available for that. Okay, point estimation. Okay, I will cover that. Time series, and I will do it by tomorrow morning, possibly. If not, because tomorrow totally dedicated for case study. At least for a time while I'll try to maintain cover the time series because if not, we'll go with the case study. Why I have chosen 0.01 is I already explained. Anyway, I will explain again that when you go with the multiple pairwise comparison, the same level of significance should not be chosen because it will incur the family-wise error rate. That's why we have to divide that 0.05 divided by the number of groups at comparison. That's why 0.05 by 5 is nothing but 0.01. Okay. How the box plot or defines in the multivariate normality? Actually, that's a good question. But there is a change here. Our objective, of course, box plot is for observing the. Oh, okay, okay. Multivariate normality. This is what we call what we say multiple box plots. Actually, multiple box plots. But our observation here is to see the variation across the years with respect to the each parameter. Okay. And then time series, we'll take it later, sir. Ankova is not covered, madam. Ankova is not covered. Who is that? I don't know. Pillai is one measure. Pillai is one measure to compare across the factors, different levels of factors. Yes, why not? We can use R for stochastic modeling. We can use R for stochastic modeling, but I'm not expertise in stochastic modeling. Okay. How to check normality assumption using box plot? I think this question is repeatedly raised. I don't know. I already explained twice. Anyway, see, box plot is the major normality using the mean, the median, first quartile, and third quartile. Okay, using the median, first quartile, and third quartile. Simple indication that the middle line, that is median, should be in the center of that particular box. Okay, and no data point should be on above or below that particular viscous. I think you are not in the starting few minutes of the session. Could you please explain Anova and Manova difference? Anova is a univariate. If I take only nasal height and compare across the years, that is what we call Anova. But here we are collectively taking multiple characteristics and comparing them across the years. That is what we called that is what we called Manova. What is the difference between reject H naught and not accepting H naught? This is the nice way of telling. That's it. Generally, in most of things, we should not say reject H naught because the probability of rejecting null hypothesis, there is a chance behind that mechanism. That's why we do not accept the null. The probability is making us not to accept the null hypothesis. That's it. So we are not rejecting it. So the probability, the chance which is observed out of the comparison is not making us to not to accept the null. We can use Hotlings also. You can use Hotlings test instead of Pillai's. Sir, for unit normality testing, we have QQ plot, PP plot, but for multivariate normal test, very good question, sir. Very good question. Sir, for multivariate normality, you can use box plot, but at the same time, you have a multivariate package. Okay, multivariate analysis package. MV, sorry, MVN package. MVN. I type here. MVN. Capital MVN package for multivariate normality testing. In this particular package, it is available in R. It is available in R, where it has three different methods: Royston's test, Jerkless test, and one more test is there. And using those, we can have the multivariate normality testing. In univariate, you do with the Shapiro-Wilk test. But in multivariate normality, you can use Royston's test or Zerkless test, which are available in this MBN package. Okay. How can I effectively apply Manova? For what situation, sir? For what situation you want to apply effectively? When your objective is to compare set of characteristics across different levels of the factor under comparison, then you can effectively use Manova. That is a chance. This is the best example. One person is claiming that there is a correction problems. It's a pure. This is the best example of chance connection, chance causes. Okay, that we don't have a control on the internet speed or connectivity. Sometimes it may happen from my side. Sometimes it may be from your side. Okay. Any other questions? So tomorrow what we do is in the morning, first half an hour or 15 to 20 minutes, I'll try to explain. I will show you one Word document, how to prepare a case study presentation, all these things. Then thereafter data sets will be shared. Today itself I will give the data sets to the organizers so that they can put across the total number of participants, so that be ready with the data sets. They are all openly available. Okay, tomorrow you start working with the codes. I will share all the things. I'll share the what and all contents we have covered so far, all the codes and data sets I'll share with the organizers. In turn, they will share with you. Okay, so that tomorrow be ready with R installed readily. Okay, and better you install R Studio also. Okay, and if you just R Studio latest version, it will give you the link to the that particular website. Go to that, choose your OS and download, and then be ready for tomorrow's case study presentation. I wish, I expect. That's what, sir. I said I also share the, I will also share the R script also. Okay. So I expect that most of you or all of you should practice it tomorrow, so that once just listening will not support you much. You have to practice. You have to practice. Then only you'll come to know where you are committing mistakes. Mistakes are correct, where should be encouraged so that you can rectify. What is maximum data analysis? Multi-dimensional data analysis or maximum data analysis? I don't know. Very new questions are coming. I don't know maximum data analysis. Okay, so hope I have covered all of your doubts starting from day one to till date. Okay, almost 99.9% I think I have covered, or 100% I can take. Okay, uh, having about asking about bootstrapping. That's what I said, 99.9. Okay, that 0.01% is in bootstrapping. Okay, there is a function, I have searched it. Okay, there is a library boot where you have to use boot.t.test, boot.t.test, and certain arguments to be given, then you can do bootstrapping with any kind of a model building, comparisons, anything. Okay, library boot is available now. Using that you can do. So that 0.01% is also covered now. What is the operation research? Operation research in R. Yes, you can do. There are good number of packages available. I have started recently learning how to compute the simplex model, two-phase simplex, big M method, transportation, assignment, very easily with a click of, with a just a one line or two lines, we can totally get the optimal solution. Very nice packages are there in R for operation research. Okay. Logistic regression model, madam, it is not in 10 to 15 minutes. Definitely it will require 1 hour, because I should cover the background and then come to that. I think I am ready to continue this with a new webinar or a new interaction program where all the multivariate techniques, it is up to independent individual to think, and I'm ready to assist you like how I'm doing with the K.B.N college, that we can do wonderful sessions on multivariate techniques separately, like logistic, discriminant, and then support vector machines, Poisson regression, okay, multiple regression exclusively, something like this. We can work for 2 to 3 days where we can dedicate to completely for multivariate techniques. Okay, I'll try to show it, madam. I mean, uh, please try to show tomorrow. Can I show for t-test, or specifically you want anything, madam? Okay, fine. Data analysis best programming languages, it mean R or Python. Sir, that kind of a comparison cannot be made. Okay, I choose, my personal opinion, I choose R. Okay, okay. To connect to me, bootstrapping, I will not completely cover the essence of bootstrapping, but I will give the gist of bootstrapping. Okay. Too many requests. Right, right. Okay. Um, we'll see that. But how to contact me is, this is my address. I will do one thing. I will share my slide which has the total details of my contact. Okay, you can see here my details. Okay, so this is my contact number. You can write to me to via statsguru@gmail.com, or WhatsApp number, or call, or WhatsApp call is 9487 609 603. Okay, hope you have noted. Yeah, fine. So we can conclude today, and tomorrow by 10:30 we'll start with how to do bootstrapping in t-test. Okay, bootstrapping in t-test, and then we'll move our case study presentation. Thank you, one and all. Tomorrow by sharp 10:30 we'll assemble again. Bye.